Welcome. This is the Chemistry, Biology, and Math Revision Hub. Today we are doing the Pearson Edexcel International A-Level Chemistry Unit 4 for October 2021, Section B through Section C. I will go to the first question. It says, question 16 says, compound X is used by mammals as an alternative energy source to sugars. X is a compound of carbon, hydrogen, and oxygen only. This is very important. So they say a complete combustion of 2.5 grams of X in dry oxygen produces 4.31 grams of carbon dioxide and 1.32 grams of water as the only product. So it means as the only products, that means there is complete combustion occurred. Okay. So they say give a reason why the oxygen used must be dry. Now remember, when this combustion occurs, let's assume the compound containing hydrogen, oxygen, and carbon, hydrogen, and oxygen, if it's burnt in oxygen to produce only carbon dioxide and water, it means if this oxygen had some water in it, this water is going to contribute to the mass of that water, and therefore we will not correctly determine the mass of water that came directly from the organic compound. So to ensure that the mass is measured correctly, we need to use dry oxygen. So I said then the mass of water from the combustion cannot be correctly measured. So measuring the accurate amount of water from the experiment is very crucial in helping us determine the empirical formula. That is why we have to use dry oxygen. Question 2 says, show that the empirical formula of X is carbon 4, hydrogen 6, or 3. You must show you're working. So in this case, what we have to do is, from the results given, we know the mass of carbon dioxide produced and we know the mass of water produced. So we can use the mass of carbon dioxide to determine the mass of carbon. To do that, since carbon has a mass of 12 basically, so I'll say 12 divided by 44 times 4.31, giving us the mass of carbon. And then 2 over 18 times the mass of water gives us the mass of hydrogen. To find the mass of oxygen, it will be the mass of the organic compound minus the sum of the mass of carbon and hydrogen, giving us 1.17788 as the mass of oxygen. So I'm going to use these three masses to determine the empirical formula. So I will position the carbon, hydrogen, and oxygen, and then position the masses below, as you can see here. Then I will divide the masses in grams divided by the atomic mass of each, as you can see here, and then I'll get the number of moles of each as that. So after getting the number of moles, I'll divide through by the smallest number of moles to find the mole ratio. And when I do that, you can see the mole is going to be 1 to 1.99 to 1.33. I can roughly round off 1.99 to 2.0. However, 1.33 is not, it's not okay for it to be rounded off. So what I have to do is find a specific number you can multiply with to convert 1.33 into the nearest whole number. And when I do that, I have to multiply by 3, giving me a 3.99. 2 times 3 giving me a 6, and 1 times 3 giving me a 3. 3.99 can be suitably rounded off to 4, so this gives me carbon 4, hydrogen 6, oxygen 3 as the empirical formula of this organic compound. Let's go to the next part. This part says, part B, compound X gave an orange precipitate with Brady's reagent. This confirms presence of a carbonate because the result of an orange precipitate with Brady's reagent shows it's a carbonate. And then they're going to say, but no reaction with Tollens reagent. Any carbonyl that gives a positive test with Brady's reagent but actually did not react with Tollens, it means it's not an aldehyde, and therefore X is a ketone. And then they say when X is added to a solution of sodium hydrogen carbonate, effervescence occurred and the gas evolved, turned lime water cloudy. This gas should be carbon dioxide, and carbon dioxide must be coming from an organic acid, which is a carboxylic acid. So the next part says the carbon-13 NMR or spectrum of X had only 4 peaks. So if there are only 4 peaks, it means there are 4 different environments or carbon-13 environments. And since the empirical formula is that, yet we have only 4 different carbon-13 environments, and we have already established one of the carbons is in a carboxylic group and one of the other carbon is in a ketone group, it means there is no other way. The empirical formula is also the molecular formula, so we can confirm from that. And when we look at that structure, we have 2 possible, from the empirical formula, which we have now classified as the molecular formula, we can produce only 2 structures. Because remember, the carbonyl is either going to be on carbon 2 or carbon 3. The carbonyl can never be on carbon 4 and it can never be on carbon 1. Because if it goes to carbon 4, then that will be an aldehyde. If it's on carbon 1, then we will not have the carboxylic acid. So it's only these two structures. So how did I come to this conclusion? I said the carbon-13 NMR shows 4 peaks. Let me use this. This means that there are 4 different carbon-13 environments. Concluding the empirical formula should also be the molecular formula. And secondly, I said formation of orange precipitate with Brady's reagent shows that X is a carbonyl. No reaction with Tollens reagent shows that X is not an aldehyde. You have to state that it's not an aldehyde and then go on to say therefore it's a ketone. Then effervescence with a gas that turns lime water milky with sodium hydrogen carbonate shows that X is a carboxylic acid, or X has a carboxylic acid group. Finally, I can say the 2 possible structures are the structures we can see here. So I'm going to continue on to the next part. Give a chemical test which would allow you to distinguish between the 2 compounds you have given in B1. Include reagents required and the results for each of the compounds. So they want us to distinguish. So we know the structures we have had are CH3, CO, CH2, COOH. And the other was a CH3, CH2, C double bond O, and a C double bond O or H. So these are the 2 suspected structures of X. However, to distinguish these 2, we have to use this one because it has a methyl ketone. So to be able to test for presence of a methyl ketone, we have to use the Iodopharm test, which is iodine in the presence of sodium hydroxide. So when we do that, yellow precipitates are going to be observed with this one, while here there is no observable change. So I said yellow precipitates will be formed when with this one here, while no observable change will occur with the other. So the methyl ketone, this one here, is going to result into yellow precipitates. I will continue to the next part. So this part says, a simplified high-resolution proton NMR spectrum of X is shown. So they've given us the NMR spectrum. So they say, explain how the number of peaks in H1 NMR spectrum together with their relative heights, their chemical shifts, and their splitting patterns may be used to confirm the structure of X. Use the chemical shifts given in your data booklet. Remember, the suspects are this or that. And when we look at all of them, we can see there is environment 1, environment 2, and environment 3 for this one. And that has environment 1, environment 2, and environment 3. So we can see both structures have 3 proton environments. So this is for the environment. And then we use the area ratio or number of protons per environment. So our area ratio, this is going to be a 3 to 2 to 1, because here we can see 3 protons, 2 protons, 1 proton. And this is still a 3 to 2 to 1. 3 protons in this environment, 2 in that, and 1 in that. Now, the thing that is going to distinguish them is a splitting pattern. The splitting pattern, for this one here, we can see this is going to be singlet, that is singlet, and that is singlet, because the adjacent carbon atom does not have any hydrogen. So since they say this is a high resolution proton NMR, it means you can see that is not, it's just a singlet. This is a singlet, and that is a singlet. However, if you observe this other structure here, this one here, you would see that this environment here is going to be a triplet, that is going to be a quartet, and that is going to be a singlet. So we can see that will not have only singlets, but there are going to be other different splitting patterns. So from here, we can confirm that the structure we are looking for is actually this one here, because it's a singlet all the way through. So I will go to how I wrote my answer. I found out that it should be this, because 3 peaks indicate 3 different proton environments. I labeled them environment A, environment B, and environment C. Peak heights indicate area ratio of 3 protons here, 2 protons here, and 1 proton there. Then the splitting patterns indicate that all are singlets. So using the n+1 rule, I hope you guys know the n+1 rule. All environments have no adjacent protons. So, of course, this confirms that. And lastly, when we look at the chemical shift, you can see there is one at 11.1, there is another one at 1.9 about there, and there is another one at 2.5, about 2.5. So it's about 2.5, about 1.9, and about 11.1. The one at about 11.1 is indicative of a carboxylic group or carboxylic acid group, which is actually present. There is another peak at about 1.9, which is indicative of this hydrogen in this link. So that could be that due to this one here. And then the peak at 2.5 can indicate a proton in this. You can see these protons here due to that. So I think this is enough information to be able to confirm that this is the structure we're looking for, because the splitting patterns agree, the chemical shifts agree, the peak area ratios agree, as well as the number of proton environments. This brings us to the end of question 16. Let's go on to question 17. Question 17, the decomposition of benzene diazonium chloride is a first order reaction. Here they've given us the reaction and how it occurs. They say the activation energy of this reaction was determined by measuring the rate constant at various temperatures. In an experiment at 333 Kelvin, the concentration of the sample of benzene diazonium chloride was measured at various times during its decomposition. The results of this experiment are shown, so we can see here the time as time is varied and how the concentration is basically decreasing. So that's what we've been given, so I'll go to the next page. They say, plot a graph of concentration of benzene diazonium chloride against time. So here what we have to do is to position the concentration of benzene diazonium chloride on the y-axis and then time on the x-axis, or you could say vertical axis and horizontal axis. The key thing here is to find an appropriate scale. Remember to label and put units, and then everything is going to be okay. So the points are going to be marked and you can connect the line through points. In my connection, I created a curve. The question we have here says, determine a value for the half-life, T1/2, of this reaction. You must show you're working clearly. Now, to be able to show the examiner the results from your half-life calculation, if you look up here, the beginning concentration is 0.5. However, for the first half-life, it's going to decrease halfway to 0.25. So a change from 0.5 to 0.25. Remember, at 0.5, it's 0 time. At 0.25, it's about 125 seconds that have passed. Now, that is the first half-life. I can see it's 125 seconds. Now, the time it takes for the concentration to decrease from 0.25 to 0.125, that is another half-life. I can see it's here. You connect from the concentration you've chosen to the curve and then look down to see the time. So I can see here it's up to 250, meaning the difference here, which is this time here, it's still 125 seconds. So because it's constant, I can confirm that the half-life is going to be 125 seconds because it takes 125 seconds for the concentration to decrease halfway. I will continue to the next part. Calculate the rate constant K for the reaction at 333 K. Include units in your answer. So they say use the expression natural log of 2 is equal to K T1/2. So here we're going to use the expression we're given, and we'll first make K the subject. So using this formula here, K is going to be natural log of 2 divided by half-life. T1/2 is half-life. So remember from the graph previously, we have found that half-life is 125 seconds. So what we're going to do here is we will substitute that into there. And then this is what we're going to have. Using your calculator, you'll find that K is 5.545 times 10 power negative 3 seconds. Or you could write it as this, but converting it to standard form, I get that as the answer. So moving on to the next part, it says the experiment described in A was repeated for 5 temperatures, and the data used to plot a graph for the Arrhenius equation in the form, this is the Arrhenius equation. So we can see this is the information given. Remember, they plotted this point, that point, that point, that point, and that point. They were all plotted, and the line was not there. So the line is was as the student were required to draw the line basically. So here we can see that the vertical axis has natural log of K, and the horizontal axis is 1/T. So the first question was asked, use the rate constant that you have calculated in A3 to obtain the data for a point on the graph for 333K. What I need to do here first is to find what 1/T is, which is going to be 1/333. Remember, this is the x coordinate I'm looking for. So it's going to be 0.003003, which is going to be about there. So about there, this point here, about that point there. So after getting the x coordinate, remember the y coordinate is natural log of k. So I calculated my k previously from above. So to find natural log of k, it's going to be the natural log of 5.545 times 10 power negative 3, which gives me this. So I am going to plot on this curve a point, which is that point here. You can see the x coordinate for that point is 0.003003, and the y coordinate is negative 5.1948. That is the point they will require us to actually plot the next question we're going to look at. They say plot your data from B1 on a graph. Of course, I have showed you how I plotted that. And then the next part says determine the gradient of the graph by drawing a best fit line. Include a sign and units in your answer. Please let me take you back previously so that we can see. Remember, this is the point we have drawn, this point here. And then I drew a line of best fit through all the points. Now, to use this line to find the gradient, you have to choose specific points along that line that are easy to tell, or whose coordinates are easy to tell. So I chose that point there because these are the coordinates, and another point here since my line went directly through it, and those are the coordinates. And I did change in y, divide by change in x. I hope you guys know how to determine the gradient when you have a straight line, basically. The answer I got was negative 13793 Kelvin. It's allowed if somebody got 13200 to 14200, because of course this is kind of a very erroneous method since many students are going to choose different points. There is an error allowed in this kind of question. But for stage, use the gradient determined in B3 to calculate the activation energy for the decomposition of benzene diazonium chloride. Include a sign and units with your answer. So here what we have to do is, remember we were given this equation, natural log of k is equal to negative EA over R times 1 over T plus a constant. You have to remember the equation y is equal to mx plus c. Remember, again, let me use another color. This is the y coordinate, y-axis, so the y-axis value should be that. The x-axis value, remember it was 1 over T, and that is the constant you're looking for. So it means negative EA over R is going to correspond to the gradient, and means the gradient you're looking for should be negative EA over R. Sorry for that. Let's go back here. It should be negative EA over R, which is the gradient we have calculated from above. Remember, you also know this value, it's 8.31. It is present. It's going to be written in your data booklet. If it's not given here, it's present in your data booklet. So EA should be 13793 times the R value, and the R is 8.31. So when we calculate, we get a positive value is positive 114.619 kilojoules per mole, and that is the answer. So based on the error that will be carried out in the gradient, because many students are going to have different values of gradient or varying values of gradient, there is an allowance of values between that and that. So I hope that helps you a lot. This brings us to the end of question 17. I will move on to question 18. Question 18 says, the hydrolysis of halogenoalkanes by alkali is a nucleophilic substitution reaction. Here is an example of a nucleophilic substitution reaction. So they say the mechanism of this reaction for primary halogenoalkanes is different from the mechanism for tertiary halogenoalkanes. Of course, primary halogenoalkanes go through Sn2, while tertiary go through Sn1. So they say describe how knowledge of the rate equations for the hydrolysis of halogenoalkanes provides evidence for the mechanisms of these reactions. They say Kali arrow mechanisms are not required. So the first part you have to talk about, of course, I said primary halogenoalkanes react with alkali through Sn2 mechanism. In Sn2 mechanism, a nucleophile that is going to be basically present, two nucleophiles will be present, or both nucleophiles will be present in the rate determining step, meaning it is in one step when one nucleophile is coming in, another nucleophile is leaving. So it will leave you with a transition state. So Sn2, both are going to be present in the rate determining step, and they will appear in the rate equation. Remember, they want us to refer to the rate equations. So the rate equation for this above, if it went through Sn2, or if it was a primary halogenoalkane, it will be rate is equal to the rate constant into concentration of the halogenoalkane and the concentration of the alkali. Again, this will be okay if it went through Sn2. It means both nucleophiles are present, the nucleophile OH and the X minus, or you would say two species are going to be present. in the rate determining step. Now, the next part we talk about tertiary halogenoalkanes. These react through Sn2 mechanism, and in Sn2 mechanism, it means we're going to produce a nucleophile. The nucleophile is going to basically break off, leaving a space or pathway where another nucleophile can attack. In this case, we are going to produce what we call an intermediate for this Sn2 mechanism. So, I said, in Sn1, only one nucleophile is present in the rate determining step, and that will appear in the rate equation. So it will appear in the rate equation as rate is equal to K Rx. Only one nucleophile will be present, so the second nucleophile will not be present because it has not reacted yet, so it will not appear in the rate equation. I hope you guys understand, because the question is asking us to refer to the mechanisms as well as the rate equations. That is why I'm trying to show the rate equations for each. This is for Sn2 and this is for Sn1. Now the concluding part is talking about whether we have an intermediate or we have a transition state. So for Sn2, remember, involving primary halogenoalkanes, a transition state is going to be formed before the product is formed. In a transition state, we will have the halogenoalkane. However, both nucleophiles are going to be present. You can see the OH as well as the X is going to be present, and this is going to be negatively charged because there is an extra negatively charged nucleophile that came in, and then this is going to be the transition state before we form the product. However, for Sn1 mechanism involving tertiary halogenoalkanes, a carbocation intermediate is going to be formed. This is because the nucleophile or the halogen will break off the carbon atom, leaving a positively charged carbon as an intermediate, and that will be expressed as this one here. So this R represents an R group with a carbon basically, which is positively charged. So this step will involve those that go through Sn1, which is basically for tertiary halogenoalkanes. So this brings us to the end of this question. As you can see, the next page is towards the end of question 18. I will go to question 19. Question 19, ethanol may be manufactured by the hydration of ethene. We can see this is ethene, that is water, of course this gas, so this is steam, reacted to produce ethanol. The enthalpy change for this reaction is given as that, and this is a reversible reaction. They say in a laboratory investigation of this reaction, 1 mole of ethene was mixed with 1 mole of steam at 150 degrees Celsius. At equilibrium, when the total pressure of the system was 50 atmospheres, 0.45 mole of ethanol had formed. The first question is, give the expression for the equilibrium constant Kp for the reaction. If we want to find the expression for that, we need to look at the components present in the equation they've given us. Kp should be partial pressure of the products divided by partial pressure of the reactants. Please remember not to use concentration brackets because this is just partial pressure, so they have to be curly brackets. So, of course, the reactants are going to be ethene as well as water, so it's going to be easy to position them like that and come up with your equilibrium constant for Kp. The next part asks, calculate the equilibrium constant Kp for the hydration of ethene at 150 degrees Celsius. Include units with your answer. So I began by writing the whole equation here, and then below the equation I stated the initial moles. Remember, they said 1 mole of ethene was mixed with 1 mole of water or 1 mole of steam. So it means initially we had 1 mole of ethene, 1 mole of water, and 0 mole of ethanol. However, when equilibrium was reached, we can see, or you could say the change that occurred, they told us at equilibrium they had 0.45 moles of ethanol. It means since the equation is 1 mole, 1 mole, 1 mole, based on the equation, it means if 1 mole of ethanol is formed, it means, sorry, if 0.45 mole of ethanol is formed, it means the original 1 mole minus 0.45 for each. So this is going to be, at equilibrium, we'll have 1 minus 0.45, giving us 0.55. And for this one, we'll have 1 minus 0.45, giving us 0.55. These are the moles of each present at equilibrium. And when we add them up all, we get the total mole to be 1.55. That is the total number of moles of all the components present at equilibrium. Now, after that, before we insert our data into the Kp equation, we need to find the mole fraction. The mole fraction is going to be the specific mole of that compound divided by the total moles. So for this one here, it's going to be 0.55 divided by 1.55. That is 0.55 divided by 1.55, and this is 0.45 divided by 1.45. 1.55. The reason as to why I did not divide this to give me a decimal number is I wanted to minimize the error carried forward, so I left them without getting the final decimal from the division. So the partial pressure should be the mole fraction times the total pressure. So for each you can see mole fraction times total pressure and mole fraction times total pressure. So finally I get 17.742, 17.742 and 14.516 as the partial pressures of each. Now I can feed my information into the Kp equation. You remember Kp is partial pressure of ethanol divided by the partial pressure of ethene times the partial pressure of water or gas water, and I have all of them here. Just substitute, use your calculator, and then you can find the answer here. The next part we need to do is to find the units. Remember, partial pressure is going to be in atmospheres. Atmosphere divided by atmosphere squared gives you per atmosphere. You need to find the suitable unit. So that is the answer here. Let's continue. This part says the manufacture of ethanol is carried out at 230 degrees Celsius and 70 atmospheres. The overall conversion into ethanol is 95%. Comment on these conditions in relation to their effect on the equilibrium and the overall yield of ethanol. So let's see here. Remember, again, let me take you back. No, I actually wrote it here. You can see here. The forward reaction is exothermic. It means it does not prefer for the forward reaction to occur at higher temperature, meaning if the temperature is increased to 230 degrees, the equilibrium is going to be shifted to the reactant side. More reactants are going to be produced, and that is going to decrease the yield. Now, when you use a higher pressure of 70 atmospheres, based on here, we can see here we have 2 moles and here we have 1 mole. Using a higher pressure of 70 atmospheres will shift equilibrium to the product side, leading to production of more moles of ethanol. So it means there is going to be a contrast between the two. So let's see what I wrote. I said the forward reaction is exothermic, so high temperature shifts equilibrium to the left, lowering the yield of ethanol. That is correct, because of course the forward reaction is exothermic and it prefers less heat or lower temperature. Then there are fewer moles of gas at the product side in comparison to the reactant side, so increasing pressure shifts equilibrium to the right side, leading to a higher yield of ethanol. That is correct. So I concluded here by saying therefore a higher temperature of 230 is used to increase the rate of reaction even though it compromises the yield. So basically there is a compromise between yield and rate, because let me give an example. A reaction can have a maybe 95% yield, but it's going to take like 24 hours for it to be carried out. But in industry, we want things to occur really fast, so increasing the temperature, provided we can get the product within a short amount of time to increase the rate of reaction. Basically, it means a higher temperature can be preferred to get the product faster. Any unreacted substances can be recycled in order for us to get the product we desire within the short time. So here I conclude by saying unreacted reactants can be recycled to increase the overall yield. So if the yield is lower due to the higher temperature favoring the backward reaction or the reactant side, we can recycle any unreacted reactants, and then they can be basically converted into products in the next cycle. This brings us to the end of section B. Let us go straight to section C. Section C, this is question 20. It says, sodium hydrogen sulfate is a widely used acid with applications that include removing lime scale as a food additive. Sodium hydrogen sulfate is a weak acid because of the presence of the hydrogen sulfate ion, as we can see here. So they're going to say, write the equation for the dissociation of the hydrogen sulfate ion in aqueous solution. State symbols are not required. So since we are working with the dissociation of the hydrogen sulfate, it's going to dissociate reversibly. So it means, because they said it's a weak acid, so basically this is going to dissociate reversibly. So HSO4 minus, reversible, H plus, as well as SO4, 2 minus. So this is really easy to do. The next part says, a solution of sodium hydrogen sulfate of pH 1.13, calculate the concentration of this solution in gram per decimeters cubed. So here we can see, remember we are looking for the concentration. What we can begin with is by writing the Ka. So Ka is going to equal to the concentration of H plus, concentration of sulfate divided by the concentration of HSO4 minus. I'm going to use some assumptions here. So we know that since this is a weak acid, the dissociation of this is not going to be that great. And we know the H plus and the SO4 minus produced are going to come from the original, which is this. So meaning they're going to be equal in moles. And since they are present in the same volume, it means they're equal in concentration. So here we can say the concentration of H plus and the concentration of SO4 minus are exactly equal. And again, they are equal because they are the same number of moles, since the mole is 1 mole of HSO4 produces 1 mole of H plus and 1 mole of that. Since they are present in the same volume of solution, it means they're going to have the same concentration. Also, we can make an assumption. The first assumption is that the concentration of HSO4 minus initially should exactly equal to the concentration of HSO4 minus at equilibrium. So this is exactly the concentration that was there initially. So let's begin with pH. Remember, they've given us that pH is 1.13. I am going to use pH to find the hydrogen ion concentration. So pH is negative log of hydrogen ion, which is 1.13. Therefore, the hydrogen ion concentration should be 10 power negative 1.13, which gives me that. Now, because I have this, and I have also concluded that that is equal to that, I can make this whole thing to be H plus squared, as you can see here. So I can go on to say Ka is equal to H plus squared divided by HSO4 minus. Remember, I know Ka, and I know that, so I can be able to find the concentration basically. So here I have substituted the Ka, and I have substituted that. Making this the subject, I come up with the answer as 0.45709 mole per decimeter cube. So this one here, again, initially it was sodium hydrogen sulfate. So in the next step, I have to multiply by molar mass because I have the concentration in mole per decimeter cube. If I want to convert it in gram per decimeter cube, I multiply the concentration in mole per decimeter cube times the molar mass. Since it was sodium hydrogen sulfate, I need to use the molar mass of sodium hydrogen sulfate. And finally, I can see the concentration of sodium hydrogen sulfate in gram per decimeter cube should be that times the 120.1, giving me 54.896 gram per decimeter cube. So that is it basically. Let's continue to the next page. Here they say, state the assumptions you have made or you have used in A2. Of course, this is easy. There are two assumptions we usually use. Number one, the dissociation of water is going to be negligible. And then number two, of course, is that this dissociation here is going to be negligible as well. So I said the dissociation of HSO4 minus is negligible, or it's really, really small, so that the initial concentration of HSO4 minus is equal to the concentration of HSO4 minus at equilibrium. We assume that the dissociation of the weak acid is really, really, really small. Therefore, the hydrogen ions produced are really, really less. The next assumption is the hydrogen ions present, or the concentration of hydrogen ions in this solution, are not due to the dissociation of water, or you could say water dissociation is negligible. So here I say H plus ion, the concentration is only due to HSO4 minus dissociation, meaning it's not due to water. So water did not dissociate. That is the second assumption. And then here we're going to say a solution containing sodium hydrogen sulfate and sodium sulfate is a buffer that is used to preserve urine for steroid analysis. State what is meant by the term buffer. A buffer is a substance that resists change in pH. That is one mark. Then the second mark, you have to say when small amounts of acid or alkali are added. Together, 2 marks, you have to talk about resisting change in pH, and then when small amounts of acid or alkali are added. So the next part here says, calculate the pH of a buffer prepared by dissolving 0.75 mole of sodium hydrogen sulfate and 0.5 mole sodium sulfate in distilled water to make 1 decimeter cube. Now here I try to demonstrate what is going to be taking place. We are putting the hydrogen sulfate and the sulfate into a total volume to create 1 decimeter cube. It means the concentration is basically going to change for each. So let's take an example. Let me use green. Initially, you can see we have those moles. Those moles are going to be present in 1 decimeter cube because combining the two solutions increases the volume to 1 decimeter cube. So the new concentration will be the number of moles you have added divided by 1, which gives us 0.575 mole per decimeter cube. And on the other side, we're going to do the same thing. Concentration is number of moles over volume, which is 0.5 divided by 1, and it's going to be 0.5 mole per decimeter cube. So this is the concentration I'm going to use. And remember, they have told us this is a buffer. So when we are working with buffers, I'm still going to use this equation, and I will write the expression for Ka, make this. But however, the assumptions we made before, I'm not going to make them because this is not coming from the dissociation of the weak acid. It's two things that are being mixed. So I have to leave the concentration of the salt as well as the concentration of the initial hydrogen sulfate that is trying to be broken down. So sulfate concentration is completely different from the HSO4 minus concentration. So to find the H plus ion concentration here, I have to make it the subject by multiplying that times that and dividing everything by that, as you can see in this expression here. So then I introduce negative log. Negative log of H is going to be pH. Negative log of Ka is going to be pKa. And the negative log of this, if you want to convert it into positive, that goes above and that goes below, which gives me the plus log SO4 minus over SO4 minus. Some of you can memorize this. Those of you who do mathematics, you know how to convert this equation into that. You can also work like this. There is no problem, but it's just saying pH is equal to pKa minus log HSO4 minus concentration divided by the concentration of SO4 minus. So here, remember we have previously we know that pKa is 1.92, so I'm going to substitute 1.92, and I have this concentration and that concentration, which I'm going to substitute here, and my final answer will be pH is equal to 1.7439. So that's it. Let's move on to the next part. Separate samples of 0.00500 mole of hydrochloric acid are added to 1 decimeter cubed of distilled water into the buffer. So we have a buffer solution, they add that amount of HCl, and water, they add that amount of HCl. They're asking to calculate the pH changes that result in each case. Assume that the volume remains constant at 1 decimeter cubed. So let's see. Remember, hydrochloric acid is a strong acid, so if you add 0.005 moles of HCl, it is going to generate 0.005 moles of H plus because there is complete dissociation. And when this occurs, the produced H plus is going to mess up the equilibrium. So basically, it's going to react with SL4, sending equilibrium back to the left side, generating more reactants. So basically, so it means if I added 0.005 moles of HCl, it is going to produce 0.005 moles of H plus. The produced 0.005 moles of H plus are going to react with 0.005 moles of sulfate, producing 0.005 moles of HSO4 minus, as you can see here. So when that occurs, it means the moles of the SO4 are going to be reduced by 0.005, and the moles of HSO4 minus are going to be increased by 0.005, as you can see here. So the initial moles before the addition, remember previously we had 0.75 moles of that and 0.5 moles of that. That is from the previous question. When we add acid, the produced HSO4 minus are going to be 0.005. So the total change is going to create a 0.755 moles of HSO4 minus, while on the other side we're going to have a reduction by 0.005, creating a 0.495 mole. Now that we have this, remember this is just number of moles. However, in finding the pH, when we use the buffer, we need concentration. Since they have told us that the volume has remained the same, it means concentration is going to be number of moles divided by 1 decimeter cube, which gives us that as the concentration, and number of moles divided by that, which gives us that as the concentration. Now that we know the new concentrations, we can just substitute them into our pH equation. So pH is equal to pKa plus log the concentration of sulfate over concentration of hydrogen sulfate. Feeding everything in here, remember we know pKa already, plus the log, this concentration, which is that, divided by that concentration, which is this. It gives us the final answer of, here we can see 1.7367. That is going to be the pH we can see. Now, if you want to find the pH change is going to be initial minus this that we have. The change is going to be 0.00721. That is going to be the pH change that we can observe. Now, let us go to the next part. We want to find the pH change of water on addition to over 0.05 mole of HCl to 1 decimeter cubed of water. here we can see there is the original pH, which is basically pH of water is originally about 7. Now, when we add 0.005 moles per decimeter cubed of hydrogen ions into this water, it is going to change the hydrogen ion concentration by the same amount. So here we can see the change, the pH or the change that has occurred is going to be negative log 0.005, which is 2.30101. This is when we add, this change here I'm talking about is due to the H plus added, not overall change. Again, let me emphasize on this. Maybe I can erase it so that you can just see. This change is because this is the pH of the hydrogen ions. This is for the introduced hydrogen ions. Introduced H plus, not the overall change that is going to occur. And then I can say here, this can be the final pH change when we subtract. So let's see here. When this is going to be the concentration of the hydrogen ions introduced, and since pH is equal to negative log of hydrogen ions, we're going to say it's negative log of 0.005, which will give us this as the answer. So this is the pH that has basically occurred within or the hydrogen ions introduced are responsible for this pH. Now the change is going to be the original pH, which is 7, minus the pH created when the hydrogen ions were added, which is that, giving us a 4.69, which is basically 4.7. That is the change in pH of water. Let us continue. Lastly, here we have, they say the titration curve obtained from the addition of sodium hydroxide solution to a weak acid is shown. They say the equivalence point E of this titration occurred at pH is equal to 8. You can see it here. So the first question says, explain the observation that would be made if methyl orange in this range were used as the indicator. So you can see the pKin is 3.7, which would be well lower. So here I said, methyl orange indicator color will change from red to orange, then to yellow. Of course, this is the observation that you'd see. And then the endpoint of methyl orange indicator will occur below the equivalence point, because you can see it's within 3.7. So if this is the equivalence point, the other its side color change is going to occur below that equivalence point, which is 8, since its pH, basically its pKin is 3.7, and the color change, and this will be below basically E. So we can finally conclude that a large volume of sodium hydroxide will be added from the start of the color change of methyl orange to the point of formation of the endpoint color in comparison to using another indicator. So basically, if we use an indicator that is going to be suitable, it means we're going to add a little amount and we're going to see a drastic change in pH in comparison to if we use an indicator whose pKin is way below the equivalence point. It means after the endpoint, we basically have to add a larger volume of the water in order for us to see the significant color change. So here they say larger volume of sodium hydroxide will be added from the start of the color change in order, so basically for the endpoint to be seen. Or you would say the transition would be longer if the pKin was below the equivalence point of that. So here I said the color change will not only occur due to a drop, there will be a gradual change in color. Yes, it's going to occur over a longer period and not within a shorter time, because the equivalence point and the pKin are further apart. So this brings us to the end of section C, as well as the end of the whole paper. So please, I hope it helps you a lot, and do not forget to subscribe to our channel. We'll keep publishing some papers so that they can help you in your revision. See you next time in our presentation. Bye-bye.